Hello, everyone, and welcome to WiCON 2021. Today, I would like to give a talk about federated machine learning for intelligent edge network. My name is Nguyen Tran. I'm now the senior lecturer in the School of Computer Science at the Faculty of Engineering at University of Sydney. And thanks for the organizer of WiCON for inviting me as a keynote speaker for this year. So the outline of my talk today, including 4 parts. First, I will introduce to you the concept of federated learning. Next, I will give you some application of federated learning, especially for edge network. And then the last 2 parts, I will give you the latest result relating to personalized machine federated learning and robust federated learning. All right, so for the background of machine learning, so first thing, machine learning, we can understand like the process of teaching a computer system on how to make an accurate prediction with the help of data. So the prediction could be, for example, a piece of fruit in a photo is a banana or an apple. Right? Or another example of prediction like spotting people crossing the road in front of a self-driving car, or make a classification task on whether an email is a spam or not, or recognizing the speech accurately enough to generate a caption for a YouTube video. So you see that have a lot of great application by using machine learning. But in traditional machine learning, that we call it a centralized machine learning, in this case, all of the data, all of the computation and communication are on the same machine. For example, like in your desk, all of them should be done on your desktop or your laptop, right? So in this case, as you can see, when you have to deal with a model, a machine learning model with big data or a complex learning task that you have to use deep learning, then you can see that the central machine learning is not a feasible solution because it's not scalable. So people think about a scalable solution, and one of them is a distributed machine learning, especially in the context of data center or the cloud. So if you take a look at this figure, as you can see, this is an example of a data center. So you can see here, there are multiple rack that can contain tens of the server. And all of those server in the same rack are connected by a very high speed connection. Typically is a wireline connection. Right? And then the inter-rack communication is also performed by using the switch or the router. Is also performing very high speed connection. Right? And then all of them, all of the rack here with inside the same building can be connected via wireline connection or high-speed optical connection. So as you can see here, all worker nodes are connected with fast communication link and with a powerful computation. Here, we can see that the solution is scalable in terms of computation because all of the tasks can be splitted and shared evenly between all the worker. So here, I mean, worker is similar to a server here. Right? So in order to do the machine learning task in a sense of logging all of the data or collecting all of the data to a central server in the data center, and then they're gonna shuffle the data and split and share all of the data evenly to all of the worker, and then each of the worker can run the computation on their data. So the solution of distributed machine learning on the cloud or data center can provide benefit of scalable computation, and it can facilitate for big data and complex machine learning tasks like deep learning. But well, there's a new scenario that people think about to protect the data privacy. So what does it mean? It means that, well, nowadays, so personal data should not be collected to a centralized server, like in the case of distributed machine learning. So we prefer some learning model or learning scheme such that the data should not be shared to a central place. Instead, the data should be kept private at each of the device or each of the worker. And then one of the technique that enable that solution is the federated learning. So which is the cutting edge machine learning technique where the model training is distributed over the IoT device or user equipment. And each user equipment contribute to the learning model by independently computing the gradient or the stochastic gradient based on its local training data. So as you can see, nowadays, with the support of the very powerful processor for the user equipment, and with the potential large amount of the user equipment or IoT device that can be a participant for the federated learning, which benefit for the enabler of new generation of machine learning over network, which is called federated learning. Okay. So one of the motivation for federated learning on, especially for intelligent edge network, is that, as you can see here, the estimate by Cisco in terms of the total amount of data that will be generated at the network edge by the end of this year by due to IoT and mobile device is this amount. So compare to the global data center traffic that we only reach by this amount. So as you can see here, there's a paradigm shift in terms of big data generation and storage from large scale data center to the edge network. And that fuels the booming trend of what recently have been is the central topic of many research that called intelligence at the edge or edge AI. And we really see that, well, federated learning is actually the key factor to boost the intelligence of the edge with the data privacy. Okay. So what could be the potential benefit of federated learning in different area? So in terms of cybersecurity, then you can see here, traditional centralized machine learning technique have to collect and log the data to the cloud, which inevitably expose the user private data, which create a problem from the viewpoint of cybersecurity and privacy, right? With federated learning, we can eliminate the need for sending data to the cloud. Thus, we can reduce the risk of personal or enterprise data to be intercepted or theft or falsified. Right? So another perspective in terms of the benefit of federated learning is in healthcare. So let me give you an example. Think about a rare disease, right? So if one hospital wants to learn some machine learning model for the prediction somehow related to this rare disease, then that hospital may find it trouble to have a efficient model or to build an efficient model because it only have a few samples of the patient because it's a rare disease. And thus, in this case, it does not have sufficient data for an efficient machine learning model. But if we use federated learning, and then we can enable the collaborative training between multiple participating hospital using federated learning, then we can have sufficient data to learn a global model, which could be useful for any prediction related to rare disease. And this method can mitigate the problem of lacking of data, and especially without sharing private data, especially, it's a medical data, which is very sensitive. Right. So from other perspective, so it's very clear that federated learning also have benefit in terms of technology. For example, in autonomous vehicle use case, you can see with a traditional cloud learning involve large data transfer and slower learning pace. With federated learning, we can have autonomous vehicle not only to protect its user data privacy, but also learn quickly and accurately on any on-road incident or reducing the accident and boosting the safety. And another benefit is that federated learning can help to reduce the latency, especially in the task for robot learning, and it will become more so as the robots emerge from the factory setting to work alongside with the people. Okay, so so we see there are a lot of benefit of federated learning, but the benefit usually comes with the challenge. Okay, and in federated learning, one of the major concern, the biggest challenge of federated learning is the statistical diversity. And what does it mean? It means that this is the case where the collaborating client, they have their data distribution, which is non-IID. It means the distribution of the client A can be totally different from the distribution of client B. And therefore, a single global model learned by federated learning by collaborating between all the client it's not will be well generalized for individual client data, because this is the case of is not one size fit all. When you learn a common model and you expect that common model well generalized to the client data, which is totally different and is unrealistic. So the question will be, how can we leverage the global model to find a personalized model that is stylized for each of the client data distribution? Right. So the purpose is that, well, we still use federated learning for a global model, because that global model will act as the reference point that exploits the abundance of the data by a huge amount of participants. But we're not stopped from that, like the traditional federated learning. We take further step by leverage the global model, and then we craft a personalized model for each of the data. And we hope that by personalized model that adapted to the client data, then the new personalized model will perform well on that client data distribution. Okay, so here we formulate with the problem optimization problem and the bi-level optimization problem. We call it a P-Fed-Me. So P is for personalized, Fed is federated learning, and Me is because our technique is based on the Morio envelope. So that's why we abbreviate is the P-Fed-Me, where you can see this client objective is a little bit modified based on the definition of Morio envelope, okay? Where, as you can see here, actually we just add in Morio envelope, there's a new regularization term where W here is a global model and theta I is a personalized model of the client I. Right? So geometrically, so you can imagine like W, the global model, is a central reference point where all of the client agree to meet, right? So let's agree to meet here at the common reference point. And suppose we have a bunch of clients with different data distribution here, right? And after agree on the point where people can meet together, then they would try to find a direction that adapted to their data distribution. And this direction exactly is the difference between the personalized model, theta I, in this case is a user 3, theta 3 minus 4 W. Okay. So that's the key idea of P-Fed-Me problem formulation. So we can have so each of client will try to find a model that adapt to their data distribution. All right. So the benefit of this approach is that it is agnostic to the inner optimizer, while some of the other approach restrict to the gradient descent, one-step gradient descent. In P-Fed-Me, thanks to the Morio envelope, this admin operator is agnostic to any inner optimizer. On the other hand, some of the other approach use the approximation. On the other hand, in this case, we minimize Fi directly instead of the first order approximation. And the also important point is that we require no Hessian matrix calculation, right? Compared to other approach which use meta-learning based approach that needs to calculate Hessian matrix. Okay, so this is some of the summary of the related work. So we show you that there's an increase of interest in personalized federated learning or multitask federated learning in recent years, based on different approaches, like based on meta-learning or based on the idea of mixing between local and global model, or some try to unify several models into a universal model that can explain different technique of personalized machine learning. All right, then from now on, I would like to give you a illustration of how the personalized federated learning operate. So do we have some key step first in terms of server? It will broadcast the global model to our client, and then our client will perform local update with personalized model. And finally, the server will uniformly sample the subset of client from model average. And this 3-step will repeat it until we reach a convergence. So as you can see here, this one is the aggregating server. So we have this is one client, this is another client, and in this example we have 3 clients. In the first step, the server sends the global model to all the clients, as you can see here. This is server send all the model to 3 clients. T here is the iteration T. And then, so each client, upon receiving W sub T, the global model at the iteration T, the client will try to find or to solve their personalized model. It's a personalized model based upon the most recent global model. And then the client also parallelly update the local model. So actually this local model is just for the purpose of updating the global model for the server in the next iteration. So this local model for the purpose of global model update, and this personalized model is actually the one that's gonna be used to adapt to the data of each user. All right, and then upon receiving the local model of our user, then the server gonna select the subset of the client. So this step is also important because the number of participants, it could be very large, could be hundreds of thousands, and if the server wait to receive for all of the response from hundreds of thousands or even million clients, it could take forever. So one of the idea is just take the subset of client and use the estimation from this subset client local model to estimate the global update for the iteration T. And then, as you can see here, all of the core 3 steps will be repeated. And then, as you can see, for this arrow, it means each of the client will run the computation on their own data to find the new local model and the new personalized model, right, without exchanging the data. So the client and server only exchange the model. So in order to illustrate that the algorithm work, so we do some experiment with this data set setting like this. And we consider 2 types of machine learning tasks related to convex and non-convex objective function. In the federated setting with 100 clients for synthetic data, 20 clients for MNIST data. And we distribute the data to each of the client by the power law. And we will compare with the one is the vanilla Fed average and the personalized Fed average based on the memo, which is a meta-learning based approach. And as you can see here, for different cases of strongly convex or non-convex objective function, we all can see that PFET-ME, which is personalized federated learning using module envelope, can outperform other baselines. All right. So the next topic after personalized learning is robust federated learning. So as I introduced to you, the key challenge in federated learning actually is that statistical heterogeneity, which is imposed because of the highly non-IID data in client device, right? So the first approach, which is the personalized federated learning, we call it the client adaptive approach, such as a personalized federated multitask federated learning. So one of the disadvantages of this approach is that when we have the new client with the unknown data distribution, then we may have to run the algorithm again to find the personalized model for each of the client. So we think about, well, is there any approach where we also learn a single model, a global model, but that global model is robust to a wide range of the distribution of client data distribution, and potentially it's also robust for the new coming or unseen client that could join the federated learning. And obviously, we should know what is the data distribution of the new client. So we call it the client uniform approach, because with the single global model that is judiciously learned by some new federated learning formulation, we hope that it can deliver a uniformly good performance, not only for our training client, but also for new and unseen client with unknown data distribution. Okay, so so our contribution is that we'll formulate a new well-sustained distributionally robust optimization to address the challenge of statistical heterogeneity in federated learning. We call it a waffle. So first, we introduced our problem formulation. Second, we will try to design a distributed optimization algorithm for waffle to follow the spirit of federated learning. And then we're going to show that, well, waffle can provide a robust generalization bound that's applicable to or unknown distribution or inside ambiguity set that we can modify or we can set according to the requirement. So we also show the flexibility of waffle in a wide range of applications, such as multi-source domain adaptation and enhancing the robustness to data distribution shift. All right, so let's go to the detail. Before we explain the core idea of the problem formulation of the waffle, some of the related work that that is notable to mention. So we talk about personalized federated learning and multitask federated learning, which is a client adaptive approach. In terms of robust federated learning, there's some work, they call it the agnostic federated learning, that design model that is robust again, ambiguity set, which is a convex combination of client distribution. On the other hand, our ambiguity set is based on the concept of well-sustained distance. Also, another direction for robust federated learning is based on adversarial training robust federated learning. So our approach is totally different, which is based on well-sustained distributionally robust federated learning. Okay, so here's the setting. We suppose we have M client that participate in federated learning, and each of the client has the data generating distribution P sub I, right? And we have the standard empirical risk minimization in federated learning as follow. Right. So we want to find a model theta that to minimize this ERM, empirical risk minimization. Here it means that the data Z sub I, I mean the data generated by client I, follow the empirical distribution of client I. And lambda I actually is the weight of each client that contribute to the federated learning process. And obviously, the more important client will have a higher value of lambda I. And we normalize the weights in which the sum of all of the weight of a client equals to 1. In standard federated learning, the rule of thumb, people usually chose lambda I equals to ni divided n, which is proportional to the amount of data that each client has. Right? For example, client n with more data with ni is large number, then lambda I will also large proportionally. So because our work based on the concept of water-sustained robustness, then we relies on water-sustained distance, which is defined here. So water-sustained distance basically is a metric that measures the distance between two distributions. For example, here is the two distribution P and Q. So you can imagine here, like this is an example of distribution P. You can imagine like this is a pile of sand with this shape, and this is a location of the sand, this pie, second pie, sorry, the whole shape of the pie of sand is like this. This is show the height of the sand in this location, next one. Okay, and then water-sustained distance is defined as finding the optimal transport mapping or optimal transport plan to move this pile of sand into the new location with the new shape for this pile of sand like this. Okay, and on the right hand side, as you can see here, this actually illustrates what is the optimal transport plan for moving from the distribution P to Q, where you can imagine, like, for example, at this location, this location is contributed by this small amount of this pie from this location, right? And then another small amount of this part stand at this location to this location at the new location of pile of sand or Q. So that basically just explain to you in a very simple way of the water-sustained distance, which is defined as the distance between two distributions, P and Q. All right. Then the problem formulation that we propose, we call it waffle, abbreviated for water-sustained distance for federated learning, is given in this slide. So as you can see here, the key difference with the traditional federated learning is we consider, well, what happened when there is an ambiguity set, which we call this water-sustained ball, and we consider, well, in the worst case where the data is shifted, the data distribution is shifted according to a distribution Q, which is constrained in a water-sustained ball, and that distribution create the most trouble to the learning problem. I mean, the federated learning problem. Here, the most trouble because it will increase the the error or the risk or the loss when we do the machine learning task. And then we would try to find a model that will minimize that worst case distribution Q. Right? And we should pay attention to this constraint set, which was sustainable, which is defined at, by the center of the board, where we choose it to be the empirical distribution of all of the empirical data distribution of the client, and the radius of the board defined by rho is the radius. And what the constraint set say is that, well, we allow that the data distribution of our client is shifted inside this board, right? And then the value of rho will determine how far that we allow for the shifting of the data distribution. And then obviously when rho equals to 0, then we have the problem becomes the traditional federated learning, where we want to minimize the ERM of FL with respect to the empirical risk empirical distribution. So the problem formulation in waffle guarantees that the model we're going to learn will guarantee we perform or the performance regarding with the worst case risk of the unknown distribution can be estimated, or the worst case risk inside the water stand board that we can define. And then the next challenge is related to the problem formulation, because with this formulation, it's not very friendly for distributed optimization point of view, because the variable here now is a distribution, the worst case distribution Q. So we relies on existing technique of the dual formulation of water stand distance, where this term is the key for us to observe that we can use it for distributed optimization, because this term will enable the decomposition across the all of the client distribution. Okay, and then based on observation, so we are able to design an algorithm in the spirit of federated learning, where each of the client will perform multiple local round in order to do the computation to learn for some local model, and send the local model to the server, and the server just aggregate the local model for a global model next iteration. Exactly the same spirit of federated learning. And one of the key results we obtain from this waffle formulation is this one, is the inequality to bound the excess risk of a model that we can learn from the previous algorithm. Right? So suppose this is a model we learned from previous algorithm, then this inequality gives us the bounds that, well, if, like, let's say Ni is large, it means the total number of data point of client I, and the epsilon is the optimization error bound is small, and this error term, which is determined by rho and gamma, which we control, is small as well, then we can see that the excess risk actually is defined here, telling us that, well, the risk created by our learned model will approach the minimal risk, that the best that we can do here, considering this is the whole error term very small, close to 0, right? So besides the most important result. We call it robust generalization here. We also have provide some guideline on how to choose Lambda. So if you remember, Lambda actually is the weights for each client. And we observe the application if by choosing Lambda, especially with the waffle, is, for example, you want to perform the multi-source domain adaptation. It means we learn the model for by using federated learning, by using waffle, we learn the model, and then we can use that model to apply for the prediction on other domain, which means domain here is like data distribution. Other data distribution totally different from the original data distribution that we use for training. For example, here Q is the new domain. Obviously, it is also empirical data distribution. So by choosing Lambda wisely, so we can shift the Wasserstein ball as much close to the new domain Q as possible. For example, in this case, we can choose the new center of the Wasserstein ball here. Then we can set a smaller value of rho such that this Wasserstein ball can cover the new domain. And then the model that we learn from the problem from waffle with this Wasserstein ball will also generalize to the new domain Q. So the benefit is we don't have to set a large value of rho. We can reduce the value of rho. So another application, but for choosing the right value of Lambda, is in how to cover our client distribution inside the Wasserstein ball such that rho is the minimum value. So if you take a look at the blue Wasserstein ball here, that exactly illustrates the scenario where we find this should be the right value of Lambda such that we can cover all of the data distribution of 4 clients, P1, P2, P3, and P4, such that rho is close to the minimum value. Right? And then to illustrate the practical application of waffle, we have done several experiments, and one of the first result we are able to show is that, well, we consider 2 scenarios: clean data, where the global model is evaluated on a given client test data, and the second one, the distribution shift data, where the global model is evaluated on client test data, which are under adversarial or interventional shift. So clean data means the data is not hampered, is not modified, and distribution shift means the data is somehow modified adversarially. So see, in the case of clean data here, remember this is a global accuracy performance, and you can see here by adjusting the value of gamma, then waffle can achieve the same performance of a federated average, Fed average. But in the case of distributional shift data, it means that when the data has been modified vertically, and you clearly see the benefit of using robust federated learning, right? Because the performance by adjusting it with gamma, performance of waffle can be better because it is guaranteed against some of distributed shift of the data. And we can explain similarly for other case here. We also give the result of the convergence of the waffle for different scenario here. And finally, we also provide a performance of waffle in the case of multi-source domain adaptation. So you see this is the domain that we train, and then we use the model. We use the model to test on the new domain, and then you see waffle can perform better than the vanilla Fed average in terms of multi-source domain adaptation. All right, so to sum up, we believe that the well-sustained, robust federated learning is a waffle, is one of the solution to time the statistical heterogeneous issues in federated learning. Definitely, there's more room for us for the future extension, like how to employ the waffle for unsupervised multi-source domain adaptation. And then, is there any way to reduce the computational complexity of finding Lambda for various applications? So most of the result in this talk is from the research outcome of our group that recently published in several conferences and journals. And you can find all of the material and the code on GitHub of our dual group, which stands for Distributed Computing, Optimization, and Learning on this link. And so if you have any question, please feel free to send us via email or via the to the conference organization. Thank you.